Everyone, Slava is not here today, and so I'm going to be the master of ceremonies. And it's a pleasure to have Jan de Gier, who is going to talk about two-tau-sep model. And welcome
All right, thank you, Daniel, and welcome everyone, and thanks for the invitation to present this work, which is a collaboration with a number of people, including some of whom are here in the audience. So Ziying Chen, who was a PhD student in Melbourne, Yori Hiki, Masato Sui, and Tomohiro Sasamoto are in Tokyo, and Tomohiro and Masato are here, I saw, as well as Michael Wheeler, who's in Melbourne. I will speak about the derivation of transition probabilities for two species models. So these are sort of rank 2 models, if you like, where you have particles of two different colors. And I will discuss two different models where we've been able to do that. One is based on UQSL3, so it's part of a family of models that you can build on UQSLN. And there's a second model, which is a little bit different, but for which we've been able to pursue the analysis a bit further. So I just want to start gently. It'll get quite technical later because the nature of this topic is that there's large formulas involved, but let me start off gently with some motivation. So we're interested in these stochastic processes of growth of a surface, and as we all know, many of you know, these models describe this sort of behavior in Kpz universality class. But the great thing is that many of these particle models are accessible through solvable lattice models, so you can actually derive lots of properties using solvable lattice models. So what is Kpz growth? Well, it's stochastic growth normal to the surface. It was first studied numerically in the 80s by Kadar, Parisi, Zhang. And the basic object you're interested in is a height function. So you have a growing interface, and you just want to describe that interface through the height function. And these physicists, they wrote down this Kpz equation, which I've written here in a box. So this equation here, where the rate of change of the height on the left-hand side is given by a diffusive term, which is the second derivative here, and a nonlinear term, which describes the growth normal to the surface, and then there is a noise term which you need to correctly describe the fluctuations. And I should say here that there is many physical realization, in particular one in liquid crystals, which is in Takeuchi's lab in Tokyo, same lab where Sasamoto is. So there's now quite well-known theorem that these sort of processes have non-Gaussian fluctuations. So the fluctuations occur on the order of t to the 1/3, t being time, rather than square root of t. So the height behaves as a linearly growing interface, and the ripples on the mean height growth are described by fluctuations of the order t to the 1/3. But you can say much more. And if you transform to a stochastic heat equation by just introducing an exponential variable z and write down the stochastic heat equation, then there are results that look like this. And many people contributed to this. There's a few key people here in the audience, I noticed. So this is not my work, but if I start mentioning names, I'm bound to forget someone. So this is just a work of a number of people. But you you can do things like this. So you can say things like the expectation value of that transformed height variable z. If you take this as some generating function, you can actually compute that using solvable lattice models, and you can write it as a Fredholm determinant this way, where the kernel of the determinant has an airy kernel. So there may be some function up front, some very simple rational function times an airy kernel. So that is a very explicit way of describing the averages of your stochastic process, of that height interface. And from here you can then derive the height fluctuations. So if we look again at the height, we know that it grows linearly. So we subtract the linear growth t, just for convenience, set the velocity equal to 1. So we know that h minus t is of the order of t to the 1/3. So dividing by t to the 1/3 should converge to a limit, and indeed it does. And you can then say that the probability that that limit is less than some number s, that's a distribution, and that distribution happens to be the random matrix GOE distribution. So this is a celebrated Tracy-Witten result. Just, I guess most of the people in this audience know all of this, but I had a slide in just to say that this is the Tracy-Witten distribution. You can write it quite explicitly as an exponential of an integral over a function u, where u satisfies the second Pangloss equation with airy boundary conditions. So this is a very explicit way of describing that distribution. Okay. So that was in Kpz. We, over the years, noticed that the same thing happens in the exclusion processes on a lattice, so the asymmetric exclusion process, for example. And so I've written that down here. So you have particles on Z that hop around. They can hop to the right with rate P or hop to the left with rate Q, but they can't hop onto each other. So, you know, if you have particles nearby, they can't sit on top of each other. So hopping there is excluded. And then what you can do, a quantity of interest would be, for example, the net number of particles, NYT, that cross a certain side Y. So you just sit at Y and you count the number of hops with plus or minus in which direction they go. And then if you take the following quantity, so I let Q be tau to the ny, where tau is just the ratio of the hopping rates, and then I transform it to a spatial derivative. So I basically take Q of y minus Q of y minus 1. So this turns out to be a convenient variable, convenient quantity. But basically it measures that net current of particles. So that quantity Q tilde you can compute. And again, that's done by people in the audience. You can write down things like the expectation of a product of those Q tildes. So you have n positions, x1 up to xn, and you look at this quantity there, and you average over the stochastic process. It turns out you can write that average as a multiple integral over things that look like this. And so we'll see formulas like this quite a lot in this talk. So what we see here is, first of all, let me highlight this part here. So that is the only thing that depends on time, e to the minus lambda t. And small lambda is essentially an eigenvalue of a one particle process, the eigenvalue of the generator of the process. This bit here is basically the one particle eigenfunction, if you like. So it's like a plane wave. It's just a number times to the power x. X is the position of the particle. So it's like a plane wave, e to the ikx. So you have to compare it to that. And this bit here then describes the interaction of between particles. So particles can't sit next to each other. They exclude positions, and that is described by these van der Waals factors here. So that's one way of understanding this, this formula. Now you can further analyze this formula. It's quite a bit of work, and you'll find eventually that if you then sit at the origin and you look at the net flow of particles there, again, it's linear in time. So you subtract the dull bit, and that then behaves again as t to the 1/3. So if you divide by t to the 1/3, this converges to a number, and then you can go much further and say, well, the probability that that number is larger than some quantity is again given by the GOE distribution function. I should say here that the GOE appears if you take very specific type of initial conditions. So there are other distribution functions can appear, GOE, for example, or other things if you use different initial conditions. But many of them are related to random matrix type distributions. By the way, you should, I guess, let me know if you have any questions during the talk. That's fine, just speak up. So as a quick summary of this introduction, what are the ingredients here? Well, we've used the integrable stochastic lattice model, and that allowed us then to express observables in terms of a k-fold integral. And once you have that, you can often do asymptotics for large k. I haven't really discussed that in this introduction yet, but we'll get to that later on by studying the Fredholm determinant. And the essential technique is a saddle point analysis, but it's quite a delicate type of analysis. And you then end up with exact universal probability distribution functions. So this talk, I will talk about a few new results that have to do with rank 2 models. So now we're going to look at particles that have different color. Again, you will be able to write down, if the models are solvable, you will be able to write down multiple integral expressions, but now there will be a slightly different form that will be derived using something called nested Bethe-ansatz. And this will lead to dynamic poles. So I will point that out during the talk, what that means. It does mean that the analysis, the asymptotic analysis, becomes much more complicated. And in one of the models, we've been able to push this through and find a combination of Gaussian and GOE modes. So that'll be the end of the talk. Okay, so let's start with the simplest two-species model, the two TARSEP. So TARSEP stands for totally asymmetric. So in this case, the models can only hop to the right. So the rate to the right is 1, and they can't hop backwards. What we do have is particles of two colors. So I have black particles here and gray particles. And they both move with the same rates forward. And the grays exclude each other, and the blacks exclude each other. Blacks can overtake gray. So it's possible that a black particle can interchange with a gray particle if the black particle is to the left of the gray particle. But they can't go back. So if the gray particle is to the left of the black particle, then in exchange is not allowed. So in summary, we've got these transition rates. Here I call 1 gray and 2 is black. So 1s go to the right with rate 1, 2s go to the right with rate 1, and then the last condition says that 2s can overtake 1s, but 1s cannot overtake 2s. So we're going to write down a transition probability or Green's function for this process. And I first need to introduce some notation. So I'm going to give the particles the coordinates, and I'll describe that by nu. So there are n particles in total, and they have coordinates nu1 up to nu(n). I'll take p of those n particles to be of color 2, and I will denote, my notation will be such that the p1 up to pm will denote the index of the coordinate nu that is of a particle of type 2. So we'll get nu, so nu pi would be the coordinate of a particle of type 2. Well, then you can write down the master equation for a stochastic process has the usual form. So the rate of change of the transition probability is given by some linear generator, linear equation, and there's an initial condition that at time 0, all the particles should be at their initial coordinates, which you can specify. So first of all, we have a free evolution equation. If you imagine that all these particles are very far apart, then they just all move one step to the right at a given time step. So the rate of change is then given by, well, if you select one particle, it will have come from the site before, and that's the positive contribution to the master equation. And then, of course, there's the exit terms, is that all particles can move out of their current position. So that's a free evolution if all particles are very far apart. To describe the interaction, you have to impose boundary conditions on this. So there are certain conditions that you need to impose when some of these coordinate nu are equal or differ by 1. And there are 3 in this case, and I've written down one of them explicitly. So there is a condition that if the ith coordinate is of type 1 and the I plus first coordinate is of type 2, then there is this condition that the transition probability where you set the coordinates equal should be the sum of the transition probability where nu I plus 1 is equal to nu I plus 1, like this. And you interchange the order of the particles plus the transition probability where nu I plus 1 is equal to nu I plus 1, where you leave the order of the particles the same. So there are conditions like this which you need to impose. So this system is solvable. This model is based on UQSO3 in some way. I won't go into that today, but it's possible to write down this the solution of these equations, G. And so I've written down here this full formula, and I'm sure this looks horrible to you, but it has actually quite a nice structure, which I'm hoping to highlight. So in this colored version, I've written in blue what you would get if you would look at just the tar set, the one species tar set, the very familiar model. So in that case, the Green's function can be written in this way, where you have a multiple integral over n variables, n being the number of particles, over a factorized kernel. And we sort of recognize the form that we saw before. There's this exponential of some simple function of z times t being time. There are these factors like some function of z to the power nu, when u is the coordinate. So this is like the plane wave. And then there are other things that have to do with interactions. Mind you that here I'm summing over the symmetric group. So this is still quite a large expansion. Actually, for TARSEP, you can write this, you can sort of compact this into a determinant, this sum over the symmetric group. But more generally, if you allow particles to hop either way, then that's no longer possible. So now for the two species model, basically what you are going to do is do something similar. In red, you have to add another level of the same structure of integral. They now something like this, something which is like z to the power of a coordinate, is replaced by something that looks like this, where you have u to the power p. So you do a basically it's like a plane wave on the indices of the coordinates. Right, so if you think for a moment that this z isn't there, this would just be u to the power p. So compare that to z to the power nu here. Otherwise, the structure of this red bit is sort of similar to the blue bit, and there is a sum over the symmetric group here of order m, where m is the number of type 2 particles. So whereas the blue bit is derived by a process called Bethe-Ansatz, the blue plus the red bit is derived by a process called nested Bethe-Ansatz. And this was already used by Yang in the 1960s to solve rank n models and the Bose gas for different symmetry classes. Finally, to implement the initial conditions, you have to tweak these integrals such that at time 0, you exactly specify the initial conditions. So this the black bit here, which does not depend on any of the permutations, on any of the symmetric groups, is there to make sure that at t equals 0, this quantity satisfies the initial condition. Yeah, so that's what the expression is after a brute force calculation. So it's still horrible, but on the other hand, it is very nice that you can write it down. And that's due to integrability or the solvability of the lattice model. So that's for arbitrary initial conditions and arbitrary final conditions. If you look at special cases like total crossing, so now I'm going to take an initial condition where all the type 2 particles are initially to the left of all the type 1 particles. So the type 2 indices, pj0, are 1 up to n. And I'm also going to ask that after time t, they've all crossed the type 1 particles. So the final configuration will be such that all the type 2 particles will be to the right of all the type 1 particles. So we call this total crossing for obvious reasons. All the type 2 particles will have crossed all the type 1 particles. And then you can, then the transition probability that I wrote down earlier, that ugly sum over 2 symmetric groups, becomes much nicer. And it is essentially given by the product of 2 determinants, one for each of the blocks of particles times the usual factors that you see in these multiple integral expressions, and then you have to take integrals over 2 sets of variables, one for each block of particles. And the proof of this formula is quite straightforward by evaluation of simple poles and determinant calculus based on the previous formula. So now we can look at total crossing events where we would just ask, what is the probability that 2 blocks completely cross, and summing over all final configurations. So we're going to sum. So what we'll do here is maybe I should draw a picture. So basically what we're going to look at is, say, if I have type 2 particles, sitting here, and type 1 particles sitting here. And so they're going to sort of wiggle up, and the type 2s, maybe I should put them in red. They will wiggle, but they will eventually overtake at some point. So at time t, let me denote time t here. At time t, all the red particles will have overtaken all the type 1 particles. And now we're going to sum over all the final positions nu. So I'm going to sum over all the final positions of the blue particles and all the final positions of the red particles, just to compute the total probability of crossing that you can have. And we do it in such a way that we are also putting a wall at positions S1 and S2. So what we're going to say is that all the type 1 particles end up between positions S1 and S2, and all the type 2 particles end up beyond position S2. And S1 and S2 you can take as fixed, but you could also think of them as scaling with time, so they could be moving walls. So we'll derive a nice expression for that quantity on the next slide. And moreover, what we could do is impose random Bernoulli step initial conditions, where we would take the type 2 particles, so the ones here, we can put them in random positions to the left, but keeping the type 1s in step close packed initial condition. So that expression will appear here. So that total crossing probability that I just said, where you integrate out all the final coordinates, is given by a even simpler expression. So once you get used to these multiple integrals, we have the usual m times n minus m number of integrals. There are some factors that are Vandermonde type factors. There is the time-dependent exponential, and there are some normalization factors appearing here, and the same for the type 1 particles described by W. And then it's almost factorized except for a determinant, an n minus m by n minus m determinant. But now there's only one determinant. In the previous case, we had two determinants. For the transition probability, for the total crossing, we end up with one determinant. And this is sort of where we're at. So we hope to further analyze this and look at the asymptotics of expressions like this. So are there any questions, or shall I just keep going? Okay. So there is another approach. So we've looked at directly solving the master equation using nested beta ansatz. But as many of you know, there's the Vertex model approach developed by Alexei Borodin, who's here, and Michael Wheeler in particular, and several others, where you describe these transition probabilities using a vertex model. So you can build a square lattice over here, where on the bottom and top, you describe the particle configurations in certain ways. So I'm not going to say too much about the vertex model approach here, other than sort of sketching what goes on. What we're going to do is put on each vertex a Boltzmann weight, and I'll describe it on the next page. Depending on the particle configuration that you find at that particular vertex. So the A's and B's are just a way of encoding particle configurations of a 1, 2, or multi-species model. And then the claim is, if you do that in the right way, the transition probability G that I described is just given by computing the partition function of this vertex model, of this configuration, of these configurations, sum over all configurations of particles with the given Boltzmann weights. And so the type of weights you have to put on are six vertex model type of weights. So they're all simple rational functions depending on the variable q, which is related to the hopping rates of your model, and the variable y, which is the spectral parameter, which you'll have to specialize later on. And so basically what you do, you look at a particular vertex, you look at what the colors are. They are encoded by I and E sub I. So you might have color I coming in and color E sub I going out. And then depending on how the colors move around the vertex, there are 5 different ways of doing that. And then for each of the ways, you get a different rational function that you have to use at that site. So you use these Boltzmann weights for each of the color configurations here. You take a big product over all those weights, and then you sum over all color configurations. And that will give you exactly the transition probability G. So then it's a theorem, and again, I said this is by Borodin-Wheeler. If you specialize these variables y in a certain clever way, and you take a particular limit, so there's this small parameter epsilon appearing here, you have to take the limit epsilon goes to 0, and with some normalization, this partition function that you have converges to the ASAP probability G. And here I'm talking really about ASAP, so not totally ASAP, but the ASAP where hopping to both directions is allowed. So that says that the ASAP probability is equal to the partition function of some vertex model, and you still have to calculate that. But there are cases for which that is easy. So for example, one of the results of Borodin-Wheeler is the rainbow crossing probability. So now we take all particles of different color. So each particle has its own color, hence the name rainbow. In that case, you can ask, what is the probability that starting from a given ordering, that after time t, the order has reversed of all the particles? And that probability is given by this formula down here, this formula here. So the probability of that happening is given by, again, a multiple integral over n integrals only, n the number of particles, the usual van der Monde factors to describe the interaction between the particles. Then there is the usual t-dependent exponential, and some other factors describing the initial and final configurations. So once you have this rainbow crossing probability, what you can do is block symmetrize. So for example, you can partially symmetrize half of the particles being of one type and symmetrize on those, and other half of the particles, or another fraction of particles belonging to second type. And in that way, you can get the 2-TASEP or 2-ASEP type of crossing probabilities by doing these partial symmetrizations on this rainbow crossing probability. So that's still a bit of work, but you'll end up with that product of determinant formulas that I showed earlier, if you do it that way. Okay, so I guess that's where I want to end with the TARCEP. And so the next part of the talk will be about a different model. So if there's any questions about TARCEP, then maybe now is a good time to ask, or at the end, that's fine too.
Yeah, and I just wanted to double check if I may. So are you saying that you get exactly the formula you showed us for two species TARCEP from this, or you get a formula for similar type? Do you know that you end up with exactly the same formula or not?
Yeah, exactly the same. Yeah.
Thank you.
Well, for the specific total crossing of the two blocks, you get exactly the
Right.
same.
Okay. Yeah.
Yeah. So for the transition probability for arbitrary initial and final conditions, I'm not sure whether the formulas are exactly the same.
I understand.
Yeah. Okay. Okay. So the next part of the talk, I want to talk about another model. It's related, but it's not based on UQSLN. It's a slightly different type of model. And the work that I'm going to talk about here has been in collaboration with Tomohiro and Masato, who are in the audience. For this model, we've derived similar formulas for transition probability and total crossing, but we've also been able to push through the asymptotic calculations. So we'll get to that. So this is called the AHR model, because it was introduced in the 1990s by Arndt-Heinzel-Rittenberg. And here, basically, it's again, it's a two-species model. And there are two types of particles, plus particles, that move to the right. So the plus particles are basically the purple particles that move to the right. And then there are the minus particles, which are the green lines or the white particles here, and they move to the left. And each one essentially moves as a TARCEP. So the pluses among themselves are like a totally asymmetric exclusion process, and so are the minuses, but they go the other way. But they are essentially still a single species TARCEP. Now, of course, they're going to meet, as they do here in the middle, and when a plus is to the left of a minus, then they can interchange place. But once they've interchanged, they can't go back anymore. So it shares some similar features as the two TARCEP model, but it's a slightly different type of model. I think the picture here explains perfectly how this model behaves. And so now, of course, we're interested now in the fluctuations of how these particles move. So the average drift is predictable, and we'd like to know what are the fluctuations in particular, sort of close to where they have just fully interchanged. In this case, it is convenient to write down coordinates for each of the species of particles. So we're not going to do this nested thing. We're going to take coordinates x for the plus particles and coordinates y for the minus particles. And then if you analyze your time evolution, you can write down the full transition probability in this form. And here you may recognize that if you just look at this bit here, this determinant, that's exactly Schütz's determinant for the transition probability of the single species TARCEP. And it should be there because that's what the plus particles do. If there were no minus particles, you would just get back the single species TARCEP. Of course, it's the same for the minus particles. If you just have minus particles, they are also a single species TARCEP. They move in the opposite direction, but that's, you know, that's just a choice. And And so basically what we have is two intercepts. And so what this describes is the product of two intercepts. Well, that would be not so interesting if they didn't interact. So there's some interaction that I described because they can interchange, but only in one direction. They can't interchange back. And to describe the interaction, there is this term, and that term couples the Z and W integration variables, as you can see. But whereas here, this only depends on Z's, and this only depends on W's. There's also the time-dependent factor e to the lambda t, lambda being the eigenvalue of the transition generator of this process. And in terms of Z's and W's, that lambda is given by a very simple explicit function. So the claim is that this is the transition probability for the AHR model. And we'd like to use this now to describe total crossing events and describe it as asymptotics. So very similar to the two-intercept case, we take a step Bernoulli initial condition. So we'll take one type of particles as Bernoulli distributed. So in this case, the black particles on the left, and the white particles are in step initial condition. And we let the system go and then ask what is the probability that these two families of particles have completely crossed. And then the total exchange probability is given by a formula like this. So if you look at it, you'll see it's again a product of intercept type of probability functions. So you have factors that only depends on Z's and factors that only depends on W. And then there's this one factor here, which is a very important one that describes the interaction between the two types of families. But the nice thing here that this is completely factorized, and that means that the usual techniques are available, well, in principle, to analyze this. Yeah, so there's one sort of a note that I'm making here that if n is larger than m, n is the number of white particles. So the number of black particles. You can evaluate this, but the interesting bit is where n is less than m, because, you know, if the black particles, because of they are Bernoulli distributed, they are further away from the origin. So there will be a certain time when all the particles have crossed the origin, and they do that around the same time if the number of black particles is less than the number of white particles. Because if there are more black particles, they take much longer for all of them to cross the origin. So the interesting regime is where the number of black particles is less than the number of white particles in such a way that they cross the origin, that they've all crossed the origin around the same time. And you can actually see that in this formula, that if you didn't take that, if you take more black particles, then what happens is that at a certain time, all the white particles will have crossed the origin, and a fraction of the black particles will have crossed the origin. But then there is still a fraction of black particles that still need to cross the origin. And so what you're going to look at in the asymptotics is just the fluctuations of the black particles crossing the origin. So it's just a single species intercept process. So the interesting regime is where n is less than m, and sort of in a fine-tuned scaling limit. And that, unfortunately, is exactly the case where this integral cannot be readily evaluated easily. Right? And I guess that makes sense because something interesting happens there. Okay, so what do we need to do now? We need to say we're going to look at, we're interested in asymptotics. So we are assuming that the number of particles grows with time. linearly in time, but then there are fluctuations that can be of the order t to the 1/3 or t to the 1/2 for both families of particles. And so what we need to do then is we have that formula, which is like some probabilities expressed as a huge multiple integral of n times m integrals over a factorized integrand. And we want to analyze this where n, m, and t are all very large. And so you can't do that directly in this formula here, but there is a trick that you can convert that formula to a Fredholm determinant. So if you could write this formula here as in a determinant way in this form, like 1 minus AB, then the trick is to that this linear algebra, that this determinant is equal to the determinant where the product of the matrices A and B is opposite. And whereas this is an n times n determinant, this now becomes an infinite Fredholm determinant where m appears as a parameter, and then you can just treat it as a continuously varying parameter. So that is the trick we'll have to use. And just to remind you what a Fredholm determinant is, so if you have some expression like this, Fredholm determinant, it's basically an infinite sum over determinant. So this is essentially the definition of a Fredholm determinant, and it has all the sort of properties of the usual determinants. And I've also written here a discrete analog. Just as a reminder for those of you not all that familiar with Fredholm determinants. But you can manipulate these expressions in convenient ways. So now the problem is, as I flagged one of dynamic poles, so one of the things that appear in when you go through this process, and it becomes quite technical, but you need to evaluate expressions like this, where you have a multiple integral over z, some function of the z's times a Fredholm determinant that also depends on z. And this kernel in the determinant is an integral over, and I've noticed that there's a mistake here, so this should be zeta. So it's an integral over a one-dimensional integral over zeta and a one-dimensional integral over w with some known function of zeta and a known function of w, and then there are some factors that depend on zeta, but they also depend on the zj that you'd need going to integrate over later. And also it's same for the w, one-dimensional integral over w in the kernel of the determinant, but that it includes also integration variables outside the determinant. And then there is this one here. This is a factor that depends on w minus zeta. So here, this is what I mean by dynamic poles. So the integral over w has a pole in the integration variable of the integral over zeta. And this is this is quite a typical sort of behavior of higher rank models. You don't have that in rank 1 models, where all the poles are fixed, like they're all like this at -1 or at -1 over zj. So in these one-dimensional integrals, the poles tend to be fixed for rank 1 models, but for higher rank models, you get these dynamical poles. And you somehow need to deal with that. In fact, I guess you can also think of this as a dynamical pole because the zj will be integration variables outside the determinant. So we struggled with this for quite a long time, and we're quite fortunate that Masato and Tomohiro found nice way of dealing with this. So if you stare at this expression long enough, and realizing that the integrals over these z variables are around the point 1, you'll notice that the dominant contribution of this integral is where the z's are all equal to 1, the zj's are all equal to 1, and that subdominant. If you move z away from 1, then those give rise to subdominant terms. Now, to prove that is really difficult, but it was mainly Masato who was able to make a big progress here. So one of the key propositions is that if that formula up there, if you put it into the Fredholm determinant definition, that if things like this, the full expression splits into two terms. One is a normal Fredholm determinant that no longer depends on these z variables. So in this determinant, all the z's have been set to 1, plus a remainder, and the remainder is of order z minus 1. And these a and b are some known functions that you can derive. So you can derive this using, essentially it's linear algebra, but it's quite a bit of work to do that. Now this bit here, the first bit, if it was just for this bit here, that can be easily evaluated using standard techniques for rank 1 models. The next problem is to show that this is actually small. So really just repeating what I said, for the asymptotics, we look at something like this, which can be evaluated plus lower order, which you have to prove that that is small. I guess the conclusion will be that this is possible, but it's really a lot of work, and I can't thank Masato enough for really going into the details and sorting this out. So essentially you do some scaling of the variables, you scale the kernel, and you write down the rescaled kernel as in this formula below, and then you can do a saddle point analysis of those one-dimensional integrals. So that's the process. And so in view of the time, I'm not gonna spend too much further time on it. Suffice to say that the naive approach doesn't quite work because of this interaction factor, but if you be more careful, you can work this out, which we do in the paper. But the thing is, you have to really go into the nitty-gritty of your contour integrals along which you do steepest descent. And then just to show you how subtle it is, here's one of the pictures from our paper where you have to choose these contours very, very carefully. But the upshot will be that where we started with the original Fredholm determinant kernel of the transition probability in a discrete form, if you rescale all the variables with time in the right way, so you look at a particular scaling limit, then this converges to a continuous Fredholm determinant, where you can take the limit and you get the determinant with an airy kernel, and from that you get a GOE distribution appearing also in this model. And I guess I should say that the variable as appearing in the GOE is this combination of variables in the AHR model, where the particle numbers and time appear here, and rho is a parameter related to the Bernoulli initial condition. So remember that we had an expression like this. Now the determinant converges to a GOE distribution. That other factor that we had that I didn't really talk about much, I of z, that converges to a Gaussian if you do a similar asymptotic analysis. So what you'll end up finally, with asymptotics of the full transition probability, it will become a product of something that is Gaussian times something that is GUE. And so that's where I conclude. In an appropriate scaling limit, we find that the total exchange probability of the AHR model is given by a product of a GUE mode and a Gaussian mode, where S and S prime are particular eigenmodes of the system. And they are given in terms of the particle numbers by expressions that look like this. And sort of that's a theorem. That's a rigorous theorem, and it yeah. Okay, so that's where I'll conclude. So what we've done is looked at transition probabilities for rank 2 models, in particular 2 tarsep, and I've given you 2 approaches: a direct nested beta ansatz approach and then a vertex model approach, and the 2 species AHR model, for which we've done the asymptotics as well. Common features are factorized total crossing probabilities in these models. In the case of AHR, we have a proof of what is now called nonlinear fluctuating hydrodynamics. So that is basically the generalization of Kpz to multi-species mixtures. I guess I want to highlight the interplay between integrability, solvable lattice models, and random matrix theory for when you do the asymptotic analysis. And for higher rank models, what we generally expect is a mix of Gaussian and Kpz modes. And we've seen that explicitly improved in the AHR model. And again, I guess the main difficulty in the analysis of all of this is the new feature for rank 2 and higher rank models are these dynamic poles in the integrand. All right, thank you for listening, and that's where I'll stop.
Thank you. Are there questions?
Hi, I had a question. So you mentioned the UQSL3 symmetry for does that was that more of like a testing remark, or does that like quantum group structure help you with the like beta ansatz, for example?
Oh yeah, absolutely. The quantum group structure underlies the integrability of these models, right? So basically these models are built on the R matrix of UQSL3 in this case, but you could do the same for UQSLN and do, yeah, and the whole fact that you can write down these formulas or do beta ansatz is because of the underlying quantum group structure.
Okay. I guess I wanted to ask a follow-up, which was my understanding is that when you look at T-set, that's when Q goes to 0, and then somehow the R matrix isn't as nice anymore. So I don't know if that's like accurate, or if there's something you do particularly when Q goes to 0.
Yeah, so what we've done is take the limit Q to 0 after at another stage. So we haven't done
okay, I see.
Right from, well, so we've done the beta ansatz without using explicitly the quantum group machinery, if you like.
Right, sure, yeah.
And we could do the nested beta ansatz, but of course it works because we know that there is an underlying quantum group symmetry. If you're proposing to really start in the quantum group there, take the limit Q to 0, but that's...
Well, that wasn't proposing that. I was just saying, like, if someone tried to do that, it'd be a lot more difficult.
Yeah.
Yeah, okay. And I guess another question, you might have said this when my internet cut out for a couple of minutes. How well does the nested beta ansatz work for like 3 T-set or 4 T-set or n T-set?
So you have to have further nesting. So you do nesting on nesting on nesting. So it's a very similar process. And yeah, it's not that much harder. It's just a lot of accounting, but it's basically the same thing. You go nesting on nesting on nesting.
Okay, thanks.
Are there more questions?
Yeah, I have a question, which is, do you have an understanding for the quantum group structure underlying the AHR model? You said it wasn't related to UQSL3, so.
No, I don't think there's an immediate quantum group. It's more, you should more think of it as putting two UQSL2s together with some additional interaction. So yeah, so it's sort of yeah, it's not simple, the model, if you know what I mean. It's not it's just built from two UQSL2s.
But there's still Young-Baxter, but there's no sort of elegant quantum group.
Yeah, that's more or less the current understanding. Yeah.
I see. Okay, thank you.
Sorry. Hi, yeah, so this is Tom Hiro. So, but about the integrability of the AHR model, of course, okay, so in our case, it is okay, but in the case of talk today, because we are considering kind of Q equals 0 case, so integrability has been known by Cantini some time ago already. But well, at least for me, one thing which is curious is that there is a generalization of this AHR model to the case with reverse exchange with rate Q. So this Q seems to be related to the usual Q in quantum groups, but for this generalized case of AHR model, integrability has not been shown. So I think this is an interesting question. So sorry, this is just a comment.
Yeah.
By integrability, you just mean the Young-Baxter, or
exactly, yeah, but yeah, yes, in the sense of Young-Baxter, for Q equals 0 case, this has been known by Cantini, but for generalized case with Q, this has not been known. But one more remark may be that for the stationary measure, it has been known that one can construct the stationary measure by so-called matrix product ansatz. So this works for general Q somehow.
Both for the AHR and for the NTSEP.
Yes, yeah.
Thank you.
Are there further questions? I'm going to